Alright, I want to look at the concept of a method developed by Newton we're going to use it for several things, but the basic idea is use it to approximate x-intercepts of curves. We're going to see that there are other uses such as solving equations and approximating the values of a root. So here we go. Let's talk about what Newton's method is first. So Newton's method uses tangent lines to approximate x-intercepts of functions. Okay, so that's the premise we're working on here. So how does this work? Let's see if we can take an example and kind of see what this looks like. So let's draw just the graph of a function. Let's draw the graph of a function. Let's say over here it's sort of approaching that x-axis is an asymptote and does this kind of thing, plateaus, comes back down and approaches the x-axis as an asymptote again. So the question would be, what is this x-intercept approximately? And so here's how Newton's method works. The first thing you need to do is you need to make an initial guess or approximation as to what this value is, and that's actually really important. I'll try to point out to you later what happens if you make a bad approximation, because it can ruin your day. So the first thing you do is you make an initial approximation. Make an initial approximation, and we'll call it x sub 1, x1. Okay. So let's say we chose let's say we choose this guy to be our initial approximation. So once you've got your initial approximation, you need to find the tangent line. Find the tangent line at x sub 1. Okay? Find the tangent line at x sub 1. And so what that looks like is, well, you've got to go find the point on the graph first. So let's make a note about what the point is there. Let's give this function a name. This blue function, let's call y equals f of x. Okay? So the point here, the ordered pair, would be the ordered pair x sub 1, comma, f of x sub 1, whatever that happens to be. So that would be the point we're working with. Okay? Then, once you've got your point, you could imagine your tangent line. Let's not use arrows on the ends. The picture's going to get a bit cluttered as we do more of this, but you can imagine the tangent line might do something like this, right? Might do something like this. Okay? And so we need to know what the equation of this tangent line is. Well, we know a point, but we'd have to know the slope of the line also. Well, the slope of a tangent line is precisely what the derivative is for. So the slope would be f prime at that x sub 1 value. So you'd calculate your derivative, you plug this x value in, and you'd calculate a numeric output that represents the slope of this line. Okay? So we're almost to the point of knowing what our tangent line is now. So the tangent line, the equation would be y minus the y value of your ordered pair, so y minus f of x sub 1 equals your slope m, f prime of x sub 1, times the quantity x minus your x value of your ordered pair, which is x sub 1. And so x sub 1, everything involving x sub 1 here would be a value, because x sub 1 represents some number, some initial choice, some initial approximation. So everything I'm highlighting in yellow would be a number, and then x and y would be the variables in this equation. And remember, I used point slope formula here to get the equation of the tangent line, because we knew a point and we knew the slope. Alright, so now we have the equation of the tangent line. Once you have that, you're going to use the x-intercept of this tangent line, use the x-intercept of the tangent line as your next approximation. as your next approximation. So when we try to approximate an x-intercept, we're looking at a sequence of approximations, hopefully getting closer to the actual x-intercept. So you can see when you look at x sub 1's tangent line, it hits the x-axis right there. And we need to know what that x-intercept is, and that's going to be our x sub 2, our second approximation. So to find an x-intercept, what we do is we plug 0 in for y in the equation of the line. Well, here's the equation of our tangent line right here, and we're going to plug 0 in for y, and then we're going to solve for x. And solve for x, okay? Now, what I want to point out before we get into that is notice that this is going to be our x sub 2, and you can see our x sub 1 that we initially guessed was over here. So our x sub 2 is closer to the x-intercept that we want right there. And we can hopefully imagine if we keep repeating this process, you can see the picture gets cluttered, but if you keep repeating this process, your tangent lines should keep pointing closer and closer to that desired x-intercept. Okay, now let's scroll down so we have room here, and let's do this process of finding the x-intercept so that we know what x sub 2 is. So when we do that, we're going to have 0 minus f of x sub 1 equals f prime of x sub 1 times x minus x sub 1, and we're trying to solve for x because that will be our x-intercept. So what we'll do first is we'll divide both sides by f prime of x sub 1. So we've got negative f of x sub 1 divided by f prime of x sub 1 equals x minus x sub 1. So all we did was we divided by this slope. Okay? The last thing to get this x by itself is to add x sub 1 over. So now we're going to have x sub 1, positive x sub 1, minus the fraction f of x sub 1 divided by f prime of x sub 1 equals x. And this will be our x sub 2. So x sub 2 will equal x sub 1 minus f of x sub 1 over f prime of x sub 1. And that's going to give us our next x value. And all we need to know are the previous x value, x sub 1, right? We need to know the function f, that's going to be given to us. And we need to know the derivative of the function f, which, as calculus students, hopefully we can find the derivative of the function. And then once we know this, we don't have to go through the process of actually finding the equation of the tangent line and then solving for the x-intercept. Okay, we don't have to do that anymore. Instead, we can just use the formula. Now, for me personally, I'm really bad at memorizing formulas for the sake of memorizing them. I'm good temporarily, but I know I'm going to forget them. So for me, I always remember this process because it's really basic. Get an initial approximation, find your tangent line, find the x-intercept, and then repeat. That's it. So I always like to derive this following formula just like we derived this formula. Okay? So the formula says that x sub n plus 1, like if you want the next x value, you calculate it by using the nth x value, the one right before it, minus f of x sub n divided by f prime of x sub n. And so you can imagine if you keep applying this formula, you don't have to do any of this work. Once you've done it once to find the formula, once you've done that, you know that x sub 3 is going to be x sub 2 minus f of x sub 2 divided by f prime of x sub 2. And so you're still using the same f function and the same f prime function. Your input is just now x sub 2 instead of x sub 1. Okay? Alright, so that is the concept of Newton's method for approximating x-intercepts, and you have to start with an initial approximation. So this formula only works when n is greater than or equal to 1. So that means you can only do this for x sub 2 and higher. Okay? So you have to have an initial approximation that's good. Now, so let's go back to our picture up here. Let me see if I can get rid of some of this red writing. Got rid of some of it. Let's see what we can do here. I'll try to put that x-axis back. Maybe something like this. Okay. And we're trying to approximate this x-intercept. So look at what happens if I happen to choose my x1 value right here. If I choose that to be my first choice, and I go look at this point and I try to create my tangent line. Now the intent of me showing you this is I want this to be a horizontal tangent line, which means that, as you can see, I've got my tangent line. The next part of the process is to find the x-intercept of this. Well, when you have a horizontal line, there is no x-intercept. So this process fails when you go to find your x-intercept. You can't do it. So that would be a bad choice for an initial approximation. Okay. Let's look at what happens if we make this our initial approximation. Well, the tangent line here, I'll try to draw it, looks something like this. Something like this. And so then x sub 2 would be right here. And you can see that x sub 2 is further away from the x-intercept than x sub 1 was. But what happens if you apply the process again? Because maybe just that first iteration was bad. Well, then we locate the point on the curve again, which is right here. I'll try to zoom in if I can. Okay. And then I draw a new tangent line to the curve at that point. So that's going to look, maybe something like this. That might be our tangent line. And the new x-intercept is over here, even further away from the x-intercept. And you can imagine if you keep following this curve with tangent lines, your approximations are going to diverge further from your x-intercept. So it's really important to choose initial approximations that will get you closer to the x-intercept, okay? So you're probably asking, how do you do that? Well, what you do is you make a guess. Sometimes what you can do is if you can sketch the graph roughly, then you'll have an idea of approximately where the x-intercept is. Another way is you could make just a random guess, and you could start applying this process that we talked about, which I'll have a different video with examples, but you start applying this process. And if these numbers, this x sub 2, this x sub 3, if they're not narrowing down to a particular number, if they're getting further away from a particular number, from any number, then you know that you need to abandon that and start over with a different initial approximation. Or in the case where we had a horizontal tangent line, f prime is going to be 0. The tangent line slope will be 0, and you're going to get a divide by 0 error in this calculation. So you're going to get an error, or your sequence of x values are not going to converge onto a single x value. Okay, so that's how you can kind of tell that you made a bad choice. Alright, so that's the concept of Newton's method. Stay tuned for another video with examples of how to do this and how to use your calculator to quickly iterate through these approximations.